Hello students, welcome back to another lecture on resonant converters. Till now we have seen some types of resonant converters in brief. We did not go into the details, just to know what resonant converters are. We also saw the basic resonant circuit concepts, in which we saw that if we have a resonant circuit comprising of an inductor and a capacitor, then it is possible to have an oscillating voltage and current which can be used to turn off or turn on the devices, switching devices at zero voltage and or zero current. Today we go into detail into the load resonant converters. Now, these resonant converters have an LC tank. They use an LC tank that results in an oscillating voltage or current that can be utilized to obtain zero voltage and or zero current switchings. Now we have two such circuits in our syllabus. We'll start with the first circuit, that is the series loaded resonant DC to DC converters. Here you see two figures, A and B. Figure A is a half bridge configuration of the series loaded resonant converter. As you can see, there is a half bridge on the input side. This side here you can see there is a half bridge. You can have a full bridge also, and the circuit waveforms and the performance of the circuit will be the same. So you will study only the half bridge converter. So on the input side, you have a half bridge comprising of two switches, T plus and T minus, and two anti-parallel diodes respectively, D plus and D minus. After the input state, there is a resonant circuit introduced, which comprises of an inductor LR and a capacitor CR. The inductor current is IL and the capacitor voltage is VC. After the resonant circuit, you have the output stage that comprises of a full wave uncontrolled rectifier consisting of 4 diodes, followed by a filter capacitor, and there is a resistive load. The inductor current IL is rectified. The inductor current IL is rectified by this full bridge diode rectifier, and that rectified current feeds the output stage. The filter capacitor CF can be considered to be sufficiently large so that for our analysis, the output voltage may be considered as constant at VC. This is the half bridge resonant DC to DC converter. The magnitude of the output voltage will depend on how much conduction time of the switches is there. You can have a full bridge configuration, as I told you earlier. You can also introduce a transformer in this circuit to control the amplitude of the output voltage, as well as to provide electrical isolation between the input and the output. One of the drawbacks of this circuit is that the load is floating. That means depending on which diodes are conducting, the output voltage can be plus V0 as well as minus V0. So that problem can be solved by introducing a transformer here. The load here is basically, the load is not grounded. If you introduce a transformer here, you can have a midpoint diode rectifier configuration, midpoint configuration, so that you can ground one terminal of the load. So depending on which switches and which diodes are conducting, you can have a number of possibilities here as far as the input voltage V'(B) of the rectifier is concerned. If the inductor current IL is positive, the current will flow through this path. It will flow from B', this diode, load, this diode, and back to B. So that V'(B) will be equal to plus V0. However, if the inductor current is negative, it will come from this diode through this path and here. So this B' will be connected to the negative terminal and B will be connected to the positive terminal of the output, so that V'(B) will be equal to minus V0. If the inductor current is positive, then either T plus will conduct or D minus will conduct. Whereas if the inductor current is negative, then either T minus will conduct or D plus will conduct. If T plus is on, current will flow through T plus and the inductor. If T plus is off, then the inductor current will flow through the diode D minus. Similarly, if the inductor current is negative and T minus is on, it will flow through T minus. But if T minus is not on and the inductor current is negative, it will flow through D plus. So depending on which devices are conducting and whether the inductor current is positive or negative, you can have a number of possibilities here. If the inductor current is positive and T plus is on, then this VAB will be equal to plus VD by 2. Whereas this VAB dash will be equal to VD by 2 minus V0. The inductor current is positive and T plus is conducting, then VAB will be equal to VD by 2, whereas VAB dash will be equal to VD by 2. Inductor current is positive, so minus V0. If the diode D minus is conducting, then VAB D minus is conducting, so A is connected here, B is connected here, so VAB becomes equal to minus VD by 2. And VAB dash will be equal to minus VD by 2 minus V0. If the inductor current is negative, and T minus is conducting, inductor current is negative and T minus is conducting, so it will flow through this path. So VAB will be equal to minus VD by 2, and VAB dash will be equal to minus VD by 2. The inductor current is negative, minus VD by 2 plus V0. And similarly, if the inductor current is negative and D plus is conducting, then VAB will be equal to plus VD by 2 and VAB dash will be equal to VD by 2 plus V0. So depending on which devices are conducting here, we can replace this whole circuit by this symbol. It is a DC source, but the value of that DC is changing to plus minus VD by 2. Or we can say that it is an AC source. That means as far as the resonant circuit is concerned, on the input side, you have an AC source given by either plus VD by 2 or minus VD by 2. Similarly, whether the inductor current is positive or negative, this output stage can also be replaced by a voltage, which is equal to either plus V0 or minus V0. So we can have a first harmonic approximation here, and then you have an AC voltage on the input side and an AC voltage on the output side, so that this becomes a linear circuit. Also, because we are using a diode rectifier, it is possible to replace this complete path by this complete part by an equivalent resistance here. Okay, we will not analyze it that way, we will analyze it according to the way it is given in the book. And the switching frequency in this circuit can be controlled to be less than half of the resonant frequency. It can be controlled to be greater than half the resonant frequency, and it can also become controlled to be greater than the resonant frequency. That gives rise to different modes of operations. Let us see the first mode, that is discontinuous conduction mode with the switching frequency less than half of the resonant frequency. So I had sent you 3 pages in which I had analyzed this circuit. Now what is happening here is, initially at omega 0 T0, we are turning on T plus. So when we are turning on T plus, the current is flowing from plus VD by 2, T plus, the resonant circuit, this diode, load, minus, and then back to point B. So the equivalent circuit, in that case will be this much, will be like this. You have these 2 points, VAB, wherein there is a DC voltage VD by 2. Then there is T plus, which is closed. This is again point A, the resonant circuit, B dash, and then this is the output stage. Where because IL is positive here, the voltage applied here is plus V0. Now the initial conditions here are that the inductor current, initial inductor current is 0 and the capacitor voltage is minus 2V0. We are assuming here that the capacitor voltage is minus 2V0. If we see that if we see the capacitor voltage after one cycle, we will see that it is minus 2V0. So the initial conditions are that the inductor current is 0 and the capacitor voltage is minus 2V0. So if you apply KVL in this circuit, we get minus Vd by 2 plus LR DIL by dt plus Vc plus V0 is equal to 0. Remember that we have assumed that V0 is constant. And one more equation that we get here is that the inductor current IL is equal to CR dVc by dt. So these are the two state equations of this circuit. Now from this equation 1, if we take the Laplace transform, then LR, Laplace transform of dIL by dt will be SIL of S minus IL0 plus Laplace transform of Vc is Vc of S. That will be equal to Laplace transform of Vd by 2. When it goes there, it becomes Vd by 2S. And Laplace transform of V0 on the right hand side, it becomes minus V0 by S. Since IL0 is equal to 0, this becomes SLR IL of S plus Vc of S is equal to Vd by 2 minus V0 into 1 by S. Also from the second equation, IL of S is equal to CR into S Vc of S minus Vc0, or it is CR S Vc of S. And if we substitute the initial condition, that is Vc0 is equal to minus 2V0, it becomes plus 2CR V0. Or Vc of S is equal to 1 upon CRS IL of S minus 2V0 by S. If we substitute this value of Vc of S back in equation number 3, we get this equation. We can keep IL of S on the left hand side. I think we have seen this when studying the basic resonant circuit concepts. I could have used those equations directly, but instead of using them directly, I'm once again deriving them. Okay. So the left hand side becomes SLR plus 1 upon CR of S into IL of S, that is equal to Vd by 2S. This goes on the right hand side, becomes plus 2V0 by S minus V0 by S is equal to V0 by S. Again, we simplify the left hand side and transfer all the terms except for IL of S to the right hand side. So we get IL of S is equal to CR upon LR CR squared plus 1 multiplied by Vd by 2 plus V0. Or Vd by 2 plus V0 divided by LR into 1 upon S squared plus 1 upon LR CR. Once again, as we had done previously in the basic resonance circuits, we let 1 upon LR CR be equal to omega 0 squared. It means that omega 0, that is the resonant frequency, is 1 upon under root of LR CR. So if we substitute that, then IL of S is equal to Vd plus 2V0 divided by 2LR into 1 upon S squared plus omega 0 squared. If we take the Laplace inverse, then IL of T will be equal to Vd plus 2V0 upon 2LR, and Laplace inverse of 1 upon S squared plus omega 0 squared will be equal to 1 upon omega 0 sine omega 0 t. I have written IL of T there. I could have written IL as a function of omega t also there. It could have been the same. Now if we see 1 upon omega 0 LR, 1 upon omega 0 LR will be equal to under root of CR by LR, that was represented previously by the characteristic impedance Z0. If we substitute that, then IL of T becomes equal to Vd by 2 plus V0 into under root of CR by LR into sine omega 0 T. Also, if you find the capacitor voltage, 1 upon CR integral IL of T dt, as we had done previously, I have integrated the current here, and this C1 is the constant of integration, and I have used the initial condition that at omega 0 t is equal to 0, the capacitor voltage is minus 2V0. If we substitute that here, we get C1 is equal to Vd by 2 minus V0. If we substitute that, and Vc of t becomes equal to Vd by 2 minus V0 minus Vd by 2 plus V0 into cos omega 0 t. So these are the two equations for the inductor current and the capacitor voltage. As you can see, the inductor current is Vd by 2 plus V0 into Z0 sine omega 0 t. That is why you see here the inductor current is sinusoidal starting from 0. Also the capacitor voltage from its initial value minus 2V0, it is a cosinusoid. At omega 0 t is equal to pi. If you find out the values from equations 5 and 6, you will find that IL of t will be equal to 0 and Vc of t will be equal to Vt. After one half cycle, inductor current becomes 0 and the capacitor voltage rises to Vt. Now at this instant, what is happening is the inductor current, which was earlier positive, has now become 0. As soon as the current becomes 0, T1 turns off. The current tends to reverse. Now how will it reverse? The current tends to reverse. So how will it reverse? It will now reverse through D plus. So as soon as T plus turns off, the inductor current reverses through D plus. Once again, I've drawn the equivalent circuit here when D plus is conducting. The assumed positive directions of current and voltage are same as before. VAB is now Vd by 2. Earlier also it was Vd by 2, either T plus conducts or D plus conducts, VAB is equal to Vd by 2. However, because the inductor current is now negative, the diodes which are conducting in the diode rectifier have changed so that VB dash B is now equal to minus V0. Earlier it was V0. The initial conditions now are the inductor current is again 0. These are the initial conditions at omega 0 T1 and the capacitor voltage is Vt. Again, if you follow the same procedure, we solved these equations just now, so no need to go into the details. We follow the same procedure, we get that the inductor current IL of t is equal to minus Vd by 2 plus V0 under root of CR by LR sin omega 0 t. And the capacitor voltage is Vd by 2 minus V0 cos omega 0 t plus C1. Again, you find the constant of integration. Substitute it, so we get the capacitor voltage is Vd by 2 plus V0 plus Vd by 2 minus V0 cos omega 0 t. So again, if we consider omega 0 t is equal to pi, and this t is now starting from T1, then at the end of one half cycle, the capacitor voltage will be 2V0 and the inductor current will be 0. So what we see here is the inductor current is again a sinusoid, but earlier when T plus was conducting, the magnitude of the inductor current was given by Vd by 2 plus V0 under root of CR by LR. Now when D plus is conducting, it is given by V0 minus Vd by 2 under root of CR by LR. So the inductor current is now negative. It is still a sinusoid. The frequency is still same. It is still operating at omega 0, but its peak value is less than what it was when T plus was conducting. Also, if we see here, the capacitor voltage from Vd, it reduces to twice V0, as it should if we want symmetrical operation. So after 180 degrees, that means that omega 0 T2, the capacitor voltage reduces from Vd to V0. The current now once again wants to reverse, but now there is no path for the reversal of current because the positive current cannot flow because T plus is now off. So until we turn on because T plus is now off, we are not turning off T plus, the capacitor cannot discharge, so it maintains the voltage and the inductor current remains at 0 till omega 0 T3. At omega 0 T3, T minus is turned on, and this half cycle will then repeat in the negative direction. Because there is a break, because the conduction is discontinuous, one half cycle of the operating frequency, exceeds 360 degrees of the resonant frequency. This is 360 degrees of the resonant frequency from here to here, and this is one half cycle of the operating frequency. So one half cycle of the operating frequency exceeds 360 degrees of the resonant frequency. That is why the switching frequency here is less than half omega 0. The average of the inductor current IL, which is equal to the DC current I0, it feeds the output load. What is important here is that in this mode of operation, the switches turn off naturally at zero current and at zero voltage. See here that T plus is turning off at this instant at zero current, and if you apply KVL and you find out the voltage across the switch T plus, you will find that it is zero at this instant. The switches turn on also at zero current, but not at zero voltage. The diodes turn on and turn off naturally at zero current. Since the switches turn off naturally, it is possible to use thyristors here for low switching frequency applications. The disadvantage of this mode is the relatively large peak current in the circuit, and therefore higher conduction losses as compared with the continuous conduction mode. So I'm stopping this video here, and in the next video we will see the continuous conduction modes. There are two continuous conduction modes. We will see both of them in the next video.